This is a brief video to go over some remarks and properties of the Fourier transform. So first of all, there is a remark that I'd like to point out. We have defined the forward Fourier transform as a bi-infinite integral and the inverse Fourier transform as a bi-infinite integral multiplied by 1 over 2 pi. What matters is that if you want the inverse Fourier transform and the Fourier transform to actually be one the inverse of the other, you need that together they need to give you a coefficient of 1 over 2 pi. Otherwise you don't come back to the same function. But other conventions, not the one we're using, but other people, redistribute this factor 1 over 2 pi between the two functions, between the Fourier transform and the inverse Fourier transform, giving 1 over square root of 2 pi in front of both of the integrals. This is possible. This allows you to, for the Fourier transform composed to the inverse Fourier transform, to be the identity again. So I just want you to be aware of this fact. Then let's have a brief overview of all the properties of the Fourier transform that we have seen until now. First of all, extremely important, is the linearity. You can distribute the forward Fourier transform and the inverse Fourier transform through sums of functions and constant multiplication of functions. Also, really interesting when you're dealing with Fourier transforms is how easy it is to take derivatives. So the Fourier transform of the derivative of f is I omega times the Fourier transform of f. Then we saw how we can construct a new type of convolution such that convolutions in the real space correspond to product in the Fourier space, much as we did for the Laplace transform. So if we define this convolution as the bi-infinite integral of f x minus xi g xi d xi, this is true. Then we checked how the Fourier transform behaves when you're talking about shifts. So when you're shifting a function by a, its Fourier transform is a complex exponential times the Fourier transform of the function itself. It's true also when you're doing the inverse Fourier transform. A shift of alpha will give you a complex exponential with respect to alpha and x. We have also seen how rescaling in the real axis gives you a rescaling in omega as well, but the opposite rescaling, and a rescaling of the full function. Let's look at some applications of the Fourier transform. The application we're going to see is an infinite beam on elastic foundation with some loading. So the beam is supposed to be straight, but you're laying it on top of springs and you put a load on top of it. So the beam is going to adapt and take a new value, u, that is the combination between the load on top and the elastic foundation at the bottom. So the elastic foundation gives you this term k that tells you how the springs are behaving, and the load on top can change over space, so it's a function of x. This allows you to model a fourth order equation that is E times I, that are some information about the beam itself, fourth order derivative of u times k, depending on the springs, u equals wx, where w is the load on top of the beam. So w can change depending on the problem you have. If you're looking at this equation, one way you can think about solving it with the techniques we have developed until now, it's a combo of characteristic equation and Laplace transform. What's the problem with that? Well, the problem is applying the Laplace transform because we have no initial value. The beam is infinite in both directions. We don't have a point y0 equals y0. So we're going to work with Fourier transform that treats the whole real interval assuming the beam doesn't swing to infinity, but it's stabilized at infinity, we can use this. So we go from the real space in which we have this ODE, we apply the Fourier transform. That means that we can write the Fourier transform of the left-hand side equals the Fourier transform of the right-hand side. Then by linearity, we can break it by the property of the derivative of the Fourier transform. We gain this term I omega, all of it to the fourth, given by the Fourier transform of u at fourth derivative. And I have replaced u by u hat, because I apply the Fourier transform, and w by w hat. Then I can solve explicitly for u hat. It's 1 over ei omega 4 plus k times w hat. And now I apply the inverse Fourier transform. That means that the solution of my ODE is the inverse Fourier transform of this fraction that I wrote. This fraction that depends on omega as a variable and that is defined over the whole real interval. So we're left with computing the inverse Fourier transform of this product. We know that the inverse Fourier transform of a product is a convolution of the two inverses. So w hat times something, inverse Fourier transform, is w convoluted with f at the minus 1 of the fraction that we have. So we're stuck with computing the inverse Fourier transform of 1 over constant time omega the fourth plus another constant. By linearity, we can take one of the constants out. We now have f at the minus 1 of 1 over omega 4 plus alpha. And we refer to the table of Fourier transforms, trying to look for something that is as close as possible to this. And what we retrieve is that the inverse Fourier transform of 2a at the third over omega at the fourth plus a at the fourth is equal to a combo of exponentials and sines. So we have to work a little bit to make our function look like that, but it's just the addition of a constant in front, so we can do it. And we retrieve this honestly ugly mess, but we can compute it. Is an exponential of a rescaling of the absolute value of x times a sine with some extra coefficients here and there. But they're all things we can compute explicitly. We call this whole inverse Fourier transform k of x. And now we have that the solution of our ODE is the integral from minus infinity to plus infinity of k x minus xi w xi dxi. This is true for any w. We didn't have to decide which one. This is actually the same function format as the Green's function, except that this is a different convolution that we're handling. But when we were looking at Laplace transform, we were getting to the same format. Formally, we can solve the problem as we did to construct a Green's function for the Laplace problem. We were replacing the right-hand side with delta x. We can apply the Fourier transform on delta. Notice that the Fourier transform of delta is 1, so we can we retrieve the g hat, the Fourier transform of the Green's function, as 1 over ei omega 4 plus k, and then we come back. That means that we can structure our solutions in the similar way as we did for the Laplace transform by constructing any solution as the convolution of the Green's function with the right-hand side. Notice that this is not the same convolution as with the Laplace transform, but the form is the same. Let's take a couple of minutes to rewind what we have done. In particular, to build a correspondence between the Fourier transform and the Laplace transform. Fourier transform is defined on R, minus infinity to plus infinity. The Laplace transform is defined from 0 to infinity and needs initial conditions, needs information at 0. This is why the Fourier transform is usually used on x, that is the space variable. On space, we also have some information on the boundedness on the infinity, usually, while Laplace is usually used on the variable t, on time. So because we have information on the initial conditions and we wonder how they develop over time. In Fourier, we cannot enter initial conditions. So let's compare our workflow between Fourier and Laplace. We have a problem. We apply Fourier or Laplace transform. We solve for u hat or for y, capital Y. We invert Fourier, we invert Laplace, and we have the solution. So the workflow is the same. And even when we want to solve for Green's function, what we do is we replace the right-hand side with the delta function. We apply Fourier or Laplace. We solve for g hat or capital G. We invert Fourier or invert Laplace, and we define u as the convolution of g times the right-hand side, or y equals g times the right-hand side. And the only thing that changes is the definition of the convolution. So our workflow, when we work with Fourier or when we work with Laplace, is extremely similar. The only thing you have to do is check which one you want to work with, and you follow through the same steps.